So once again, I think we'll go from the end to the beginning. That's saving the best for last, perhaps. We're certainly not going to put the best first. We had a tiny little session of which I was the moderator about collaboration and interdisciplinary research. And quite frankly, we had heard a number of things about this throughout the day from some of the other commentators. Dave Waltz has probably got more to say about this than I do by several orders of magnitude. The one thing that we did kind of hit on is that obviously a real challenge and an important strength of NSF is being able to work out interdisciplinary challenges or interdisciplinary research across the directorates, and there needs to be a way to do that. It's never been entirely smooth at NSF. Obviously, it seems to me in sustainability, especially since IT is primarily an enabling technology, we have to figure out ways to do far better. The one area where perhaps even just the computer types can do better by themselves is in working with industry, where the industry is the key collaboration, and there's only one NSF player involved, which then simplifies things. But there's a lot of tried and mostly true techniques for involving industrial folks, visitors to academia, reverse visitors, internships, externships, et cetera. And this seems, especially for those areas of sustainability where there is important industrial activity already underway, this seems to be something that we should encourage, partly because, as was mentioned by several of the speakers, that you don't really understand the problems until you're out and contacting them in the real world. I know the computer types, we all love abstraction, and it has its place. But when it comes to do engineering, I'm sorry, you can't just sit there and abstract forever. You have to get your hands dirty. So, if we're going to mean something in the sustainability world, we can't sit in the ivory tower. So that concludes item G very quickly. So we'll go on then to F. Doug, are you prepared to say something?
I am.
Excellent. Or you're your agent.
My avatar, yes. So I was the chair of the Computing and Education Group, and again we had a very interesting discussion. We distinguished at the beginning taking CS to sustainability education, and also taking sustainability to CS education. Those began as two separate threads and merged eventually into a single thread. But the first thread, taking CS to sustainability, putting ourselves in a position where other areas recognize the importance of computing and dealing with the complexities of sustainability, so that CS simply isn't regarded as a service but is integral to the sustainability problem. We asked whether sustainability should be regarded as a separate field, or whether it was transcended of fields, whether it was transdisciplinary and should be part of every field. And then how would you design a curriculum to include sustainability? Would there be one sustainability school or the department, or would you work to distribute sustainability into each of the existing majors on a campus, for example? We also talked about K through 12 education to some extent, and graduate level education as well as the undergraduate level. We spoke a good deal with quite a few examples of how computer science courses could be redesigned with sustainability in mind, or modified, designing software, workflows, algorithms with environment, energy, and future orientation in mind. We've taught various courses ranging from database to HCI, and we all had ideas about how you could distribute, or parallel computing, how you could distribute sustainability in those fields. We talked a good deal about sharing data sets, sharing other resources like problem sets, and other intellectual property that might emerge, and what kind of mechanisms we thought would incentivize the sharing of such material, and the keeping of repositories that people across all college campuses could use. That's it.
Randy?
Our group was called eScience, which I morphed into a general discussion about the role of data sets and how you collect them and what you use them for. and sort of partitioned into three different categories relevant to this discussions. One is things of the natural world, so things, databases that represent things about the climate or environment that you're trying to collect, model, make use of. Another would be data sets involving human behavior and where people are and what they do and what their preferences are. And then the third being data sets involving constructed objects, whether that's a building, a bridge, or the electric power grid. And each of these has very different considerations. So in particular, the human behavior one, there's a lot of really interesting research to be done about what people are, what their preferences are, but there's this huge, gigantic problem of privacy and the ability more and more with sophisticated algorithms to re-identify supposedly anonymized data sets and things like that is just this real stumbling block. And so right now, for example, at Microsoft, they've been able to do some really fascinating studies involving tracking what their employees are doing or what people are sending via email and things. But to make that available to us, the larger scientific community, is almost impossible. And so that seems to be just a really stumbling block that it's hard to say. We had an interesting discussion on the smart grid as sort of this issue of if you have this meter that can be data mined to figure out when you're at home and when you're not and what your preferences are and so forth, the risk of that and the idea of then aggregating at, say, a neighborhood level to try and make it so that your individual behavior was not visible. And there's really interesting questions there about, is that good enough? Is there any scientific basis to that kind of aggregation that you could say it really is doing a decent job? And I think there'd be very interesting studies and analysis of that, although again, you have to have the sort of ground truth data sets to be able to work from, and somehow that you have to do that in the context of privacy. So I think a lot of these really interesting questions about people, this is sort of one of the major issues to be faced. On the constructed object side, the interesting thing is these aren't totally natural phenomena, so on aggregate they seem to have some statistical properties and random behavior, but underneath them all they have some determinism to them, and so it's hard often to make inferences about them and or even understand things like where there's potential feedback loops in the system and things like that. So we had quite a discussion about a number of other issues related to that, but I'd say those are the most important.
Prashant?
So our breakout group talked about building energy efficiency and usage. So the discussion revolved around 4 dimensions: the type of buildings, office, commercial, homes, the type of resources used in a building, gas, electricity, water, things like that, supply versus demand side issues, and monitoring versus control. Let me elaborate on a few of these. So in the context of office buildings, we saw an opportunity as a group because these office buildings are already, or your employer is already tracking who comes in, who goes out using swipe cards. The buildings are already instrumented with occupancy sensors and whatnot. We figured that there is an opportunity to put in a lot of instrumentation and not have to deal with as much of privacy issues that might come up when you try to instrument homes and share that data with electric utilities and so on. So it was felt that you could actually push the use of IT and IT optimizations in office buildings a lot faster than you could do in homes. The context of homes, we sort of came up with the issue of how does the consumer express their preferences. When you cannot even expect people to program their VCRs, how are they going to program this energy dashboard and express what they want the system to do and how to optimize energy usage? So in the interface that you present to the user is something that is just as critical as the algorithms that will actually do the optimizations. So in the context of commercial buildings, again, there are building management systems or BMSs that heavily instrument all of the tracking of energy usage in buildings. But the problem is a lot of the sensors are misconfigured, a lot of the data that's being collected by this BMSs is faulty. So coming up with better anomaly detection techniques, keeping the human in the loop, not just automated techniques, was another issue that we discussed. So we spent quite a bit of time talking about how energy storage can be used in buildings to flatten peak usage. This was something that's more futuristic. So the idea is you actually have batteries that are either in devices or in buildings that can actually be used to flatten the actual draw from the grid during peak times. And this is not that far out in terms of thinking, because if you look at emerging countries where the grid is a lot less reliable, many homes already have inverters, which are essentially UPS systems with batteries, and there is enough battery storage in there. So you can actually tap into those batteries not just when the grid is out, but when the grid is facing stress and sort of draw from the battery. So IT optimization on how to charge these batteries, when to draw from them when the grid is under stress was another interesting point of discussion. We talked about what are the cost of these batteries, how feasible is it commercially to put them in, can we also use renewable energy sources to also flatten some of the peak demand. But there the problem is when your solar panel is generating electricity, may not be the same time as when the grid is under stress. So how do you time shift this energy usage using storage? We talked about design of smart buildings. Is there a science behind this? And is there something, are there issues that go beyond just monitoring and sensors and control? One issue that came up was adaptive envelopes for buildings. So these are building envelopes that change their behavior based on the weather patterns, the temperature and whatnot, and how can we use IT and computer science algorithms to do this adaptation. We talked a lot about social aspects of how you can use social aspects to reduce energy usage and encourage conservation. So how can we share neighborhood level information to spur consumers to reduce their energy usage if they are not as good at conserving energy as your neighbors. So we felt that social networking issues or social networking tools can be brought to play here to encourage greater energy conservation. We also talked about this notion of microgrids and how renewable energy sources can be used across a group of homes. So if you are generating surplus energy, you can actually share it with your neighbor and have them use it rather than feeding it into the grid. What kind of infrastructure is needed for that? Will regulations permit this? Because you will be using the wiring that may be shared with the utilities and so on. And that led to a discussion of general discussion on multi-building optimization. Not just optimizing the energy usage of a building, but doing so of a group of buildings, maybe owned by an organization in a campus, or maybe it's a neighborhood and a group of homes. And the last issue that we talked about was that sort of went beyond electricity usage. We talked about water usage, usage of gas, and other things, stuff like air and HVAC usage in buildings. So in the context of water, basically it's not a renewable resource, but it's a resource that is likely to be stressed. So we talked about how can you design self-sustainable buildings that can recycle water, that can do rainwater harvesting, that can do other optimizations to conserve water as well. And so what are the optimization techniques there? How can we draw upon insights that are already known from electricity usage and optimizing electricity usage? And the last point was basically also a discussion on optimizations. What optimizations can be done across spatial scales and temporal scales, and how IT can play a role in that. So that's basically it.
Okay, we had a smart grid session. We talked about where is the smart in the smart grid, And the question is whether it's sort of a centralized system that has lots of sensors and figures out the whole state of that, and then that's where the smarts are, or whether it's distributed, whether there's intelligence in a lot of different places to make local decisions, or whether maybe the whole system is smart because it's a smart design and adapts appropriately. I don't think we had any good answer, but I think we talked about the smart grid as generally a response to the need to keep the lights on, but without building vastly more infrastructure to do so. This is possible because there's excess capacity in the grid most of the time, and you mostly have to worry about things like peak shaving. That is to say, you somehow have to keep the lights on despite creeping overall load and the fact that there are times when it's really, really heavy. So how do you do that? We talked about who benefits from this, whether it's designed for the utility, the benefit of the utility, the benefit of the customer, for groups of customers, or maybe a population of a region. What needs to be done before building in terms of simulation, testing, and validation? A lot of this is difficult to do because the whole system has to operate, and each piece has to be realistic. It has to be also done to scale in some way, which is difficult, tricky. The testing also has to be done in such a way as to assure operation despite stochastic bad things, weather, wind, lightning, strikes, snow, heat, associated heavy loads, energy price spikes and fluctuations, human error, terrorism, fires, failures, and failure cascades, human users gaming the system for their own economic benefit, system components aging, load creep. There are a lot of things that somehow have to be taken into account, and you have to be assured that it's going to continue to operate despite these things. That kind of simulation is something I think we really don't know how to do very well, and certainly is a big computational challenge, engineering challenge. How do we simulate the actual operation? This is the moment-to-moment operation with the possibilities of things like eddy currents, which can be heavy loads without any load being delivered. It happens. Something that power engineers know about, but there isn't much power engineering in the country anymore. The electrical effects of uphill power flow when you start putting power back into the system. What would happen if you actually put more power in than was necessary for that subpart of the grid? Where does it go? What does it do? And also human and program demand fluctuations, possibly synchronized. If everybody feels that power is going to get much cheaper at some point, they might all tend to use it at the same time, which could cause possible instability effects. We don't know. How do we simulate that in a way that we can assure ourselves that we can operate? We talked about control of usage by social pressure. What other people know about their own and others' usage would affect the way they act and what we think of them. Talked about possible mitigating things that could really help smooth the loads out and make things easier, such as microgrids, smart large buildings, which can almost be microgrids if they're big enough, grouping campuses or neighborhoods together to have a sort of shared microgrid-like area, fleet electric vehicles, which could serve as storage backbones in certain circumstances, storage super batteries that could be placed somewhere within a system. Where do you place them? That's the interesting question. Use of things like hot water, ice, or steam that can be generated in off-peak and then stored for later usage. All potentially, these are all potential things for mitigating peak load. We also had a brief discussion about looking, similar to the previous one, of looking at other things as similar to this, for instance, water systems as being somewhat analogous and in need of the same kinds of discussions, especially in parts of the country where water is scarce. Also sewage and gas was mentioned and so on. So that's our report.
Okay.
Filling in for Carla. Our group talked about basically climate and environment, and we basically looked at two different issues, one related to the monitoring of the environment and climate and to understand its impact on biodiversity and ecosystem. And the intent is that a lot of opportunity for information technology to be able to help in quantify the impact of the variation in the environment on the species of various kind. And you saw some examples earlier in the talk after lunch. And there are a number of possible advantages of such kind of research. And one, of course, is that as the people, the society becomes more aware of the changes in the ecosystem, it might help them be more willing to change their attitude, their behavior. Another very concrete example is in the context of actually mitigation, which is reducing the greenhouse gas emission. We have a lot of rainforest still left. Quite a few have disappeared, large fraction of them, and yet we are losing as much carbon from these rainforests as we lose from the entire transportation sector, cars, planes, trains, everything combined. And if you could stop that, it has immediate impact on reducing greenhouse gases and, of course, side benefits of improved biodiversity, and forests, of course, do a lot more than just store carbon for the world. So there's a big program called, from the United Nations called the UN RED program, reduction in emission from reduced degradation and deforestation of forests. And and again, that's the only one thing that they agreed on at the Cancun Climate Change Summit 6 weeks ago. And again, information technology could provide technology for monitoring the state of the global forest cover, which could greatly help in the implementation of the UN RED program. Another example that came up in our discussion was health. That is, as there are variations in the climate, it has impact on people's health. For example, if the change of snow, at the time of the snow melt changes, it has impact on allergies and such. There's a big opportunity for the citizen science in this area as the data sets for monitoring of the environment and climate become available. People can go and modify them, upload pictures. They could critique them. They could make them more complete, just in the same sense as people have gone on to OpenStreetMap on Google Map. Google Maps for United States are pretty complete, but there are a lot of parts of the world where they're very incomplete, and they have been made more complete by having just volunteers sign up and then uploading information. So there is a lot of opportunity for us to provide the initial structures that other people can latch onto. And again, these are the data sets that could be constructed using sensor network, a lot of which are being developed by our community, and by using the data from satellite, which is being available from many, many different communities, especially the remote sensing community. Another topic that came up, and I'll just take one more minute, is the interaction between environment and human, and understanding its complex nature and its sometimes fairly complex impact. And one example came up was somebody from Seattle talked about the fact that there is a financial incentive in Seattle for urban stormwater management systems. So people have rain gardens, water harvesting, and then they have this bucket sitting outside their houses, and sometimes it could could be having an impact on the pollution, impacting the quality of the aquifers. The other example that came up was the very interesting interplay between the biofuels and the rainforest. The price of gasoline went up 2 years ago, 2.5 years ago. That made biofuels a lot more attractive. That made price of corn go up. People started planting more corn, switched from soybean. The soybean price tripled. And as a result, there was a huge deforestation upsurge in Brazil in rainforest. And these are all complex interactions, and we need to develop, the term that was thrown was the integrated understanding of these coupled social natural systems, and because they interact in many, many interesting ways, and sometimes things that are well-intentioned have unintended consequences. Yes, that was it.
So our group talked about transportation logistics.
was a lively group. We had 11 people. Came up with a set of research topics and other ideas. One of the first one was the next generation intelligent transportation systems that would integrate real-time data, historical data, and predictive models. And one of the things those models would have to predict is how the driver would react to the rest of the information. Also, the evolution of intelligent vehicles, the notion of special lanes for different levels of capability in different vehicles. And then the third was multimodal public transportation systems, and the idea that you would coordinate a series of hops from your source to your destination for first your zip car, then your bus, then your subway, then your bus, but they'd be all coordinated so that you would seamlessly go from one to another. And also that included real-time information for users of the system so they understand and can have reasonable expectations and not uncertainties about whether they just missed the bus and have to wait an hour. Research issues for all of those topics. One is the scalability of local demonstrations to widespread use. So once you've got a demonstration that works in a neighborhood or a part of the city, how do you scale it up for the whole city? There's also the issue of users' privacy desires versus providers' revenue maximization desires. And so you're giving up your information to get some service. They'd like to use the information for other things you'd rather they didn't, instead of a trade-off there. Also, understanding better the factors that affect the use of public transportation systems or the embracing of smart cars and smart highways. What's the trade-off between convenience, safety, time, efficiency, et cetera? Some specific ideas, we've talked about supply chain efficiency. One was to use IT to enable economies of scale at low volumes. So for example, you could get locally produced produce for the same price as mass-produced produce because the economy of scale was achieved at a lower volume. That's a problem right now where basically the food that comes from several thousand miles away is actually cheaper than the food grown down the street because of the lack of economy of scale. Coordinated transportation services for the elderly. Consolidation of shipping. One really great idea came up that you'd go to a local place in your neighborhood where you pick up your mail and your packages, and like they would call it like the post office. Smart vehicles capturing pre-accident and accident data so you could actually reconstruct what happened. The other thing we talked about was the immutability of security theater. I was sort of hoping that we could use IT so that when I went to the airport, they would say, oh, it's you, we know you, go ahead right in. But I learned that the public wants it to be slow and sluggish so they'll feel like they're protected. I didn't know that before. There seem to be two big trade-offs in all of the stuff we've talked about this morning and this afternoon. One is that we have all these ways of increasing our system performance, and what that does is encourage greater use of the systems, which leads to needs for increased performance. This seems to be undermining sustainability. By making the systems more efficient, easier to use, less expensive, we use them more and actually consume more. So there's a bit of a dilemma there. The other is the increased convenience requires us to provide information that may compromise our privacy. And as Ed said, once foregone, privacy is difficult to recapture. So those seem to be two big trade-offs that underlie a lot of the ideas we've been talking about. And that's it.
Okay. Well, I noticed that when cocktails as opposed to lunch were at the end, things went faster. So it's been a long day. Thank you all for your patience and for starting early. A couple of observations. One is we haven't heard much about big IT problems. So this afternoon's breakouts were titled with essentially sustainability application areas or research areas. And what I heard in the last bit was a nice list of potential application areas, but not necessarily those where there are important unsolved IT problems. There may be some, but let's try to tease them out and figure out which ones might demand extra attention. And there probably, my guess is amongst all of you, there are a few dozen more that could come out as you think about it overnight and so on. So we will try tomorrow to focus on bringing out some of the bigger IT problems. Yes, Bill. So tomorrow in the morning, we have two speakers. Bill Tomlinson, I hope, will be recovered, and Carla is talking. And then we were planning to have another breakout session with topics to be determined. The organizing committee is going to meet tonight and in its infinite wisdom figure out what those might be. And, well, that's the Uber topic, right? That's the whole ball of wax. We might instead choose to have a plenary discussion about something like big IT or some other particular topic that might happen. And then in the afternoon, we're all going to meet together to try to figure out what the most important, what the kind of the bigger, the highlights, the tall poles in the tent are. And we will stimulate that with some provocative proposals, or at least an outline. Absolutely. And send mail to Irwin right away, or buttonhole him at the reception, or anybody on the organizing committee. We'd be delighted to listen to ideas. That's a good one. We need lots of those, if you will. So, the reception itself is from 6 to 7:30 on the 11th floor. I think that's a unique destination, meaning there won't be 7 doors and you have to pick which one the lion is behind and which one the drink is behind. But at any rate, that's where the reception is. And you have a little break till then. And we'll see you tomorrow morning at what time, Irwin? I think it starts a little later. All right, well, you have your song sheets. You know what to do. At any rate, thank you all very much. You cooperated beautifully with our lightning schedule today. Thanks.